Okay. It's 1 o'clock. Can you all hear me? Everybody?
Yeah.
Okay, good. Now I put in OneNote a PDF file, or it's really PowerPoint, but I changed it to PDF so I could put it up there. And oh, I got to share the screen. 1 second. And you should be seeing a shared screen right now, hopefully.
Have Ghost on.
Excuse me? I couldn't hear you. Can you all see a shared screen right now?
Yes, I can.
Okay. The PowerPoint should have came up, but it didn't. I'll just open this. This is a PDF. The PDF that I think I'm going to open it. Sent you. Can you all see this, class? I assume you can.
Yes.
And if you can't, please let me know. Now, what I wanted to do is just use this PowerPoint for one reason: to sort of springboard into problems based on. This is a pretty good PowerPoint, and I don't think you'll have any trouble understanding it. I'm going to go through it with you. I was starting this in the actual office hour. Hang on for 1 second. This thing is fussy. All right, but what I'm going to just tell you about is steady state power analysis is really what we're going to be talking about. You've talked so far about current and voltage, finding voltage division, and this would be in the AC domain too, continuous or at a constant frequency other than DC. We're not talking about transient power analysis primarily. You all follow me on that? And if you want to, you can take yourself off, I guess, muting your video. It's probably easier to nod your head than go for that thumbs up button, but you do what you need to do. I'm just trying to interact as much as I can. That's one of the things I think that Zoom really takes away from an in-person class. Now, we did a poll last time, and in fact, most people want Zoom, so that's the reason I'm doing this, but I'm willing to do whatever it takes to help you guys. All right, next, can you all see what's up here? And if you want to, just open your PDF file. I'm doing it in PDF because real PowerPoint may have some things that this doesn't. Are you following me, class?
Yeah.
Now, here's the deal. If you have a voltage and a current into anything, that Z can represent a light bulb, it can represent a factory, it doesn't matter what it is. But there's a known voltage and current. Then the instantaneous power, and I'm assuming you can see my hand here on this cursor business. Now, you don't have to write this down, Joseph. This is on a PDF. You can ink your PDF if you want. Y'all know how to edit a PDF file? You can do this very easily and quickly. But anyway, or print it out and just write on it if you want. This is the instantaneous power. It's voltage times current. The voltage is always taken plus to minus across the element. The current is into the positive terminal. Do you follow me? Now listen carefully. If the current was coming out and the voltage was positive, you would actually get a negative value for power. Do you all see that? Think about this, right? Suppose there's a voltage plus to minus, but current's leaving. Then effectively, wouldn't we have a negative power because the current would be negative, whatever it is, times a positive V. Do you all follow me? Just, you with me on this? Now, what that means is that the concept of negative power is actually a supply. Look over here at this voltage source. Think of that voltage source as a battery. Batteries supply power, right? They can dissipate, but primarily they supply power. With me? I don't know why this is so darn dark. Okay. Are you with me, class?
Yes.
Now, oh, Jessica, you didn't yell at me to make you a co-host.
Yes. Can you also make Joseph? Because I think the space on my computer is running a little short. Just
sure. Would anybody else like to be a co-host? Callan, John, Luke, Dylan. There's only guys here. Maddie, did you send me something about COVID, or is that somebody else? Somebody sent me a thing just seconds ago. I saw it pop up about COVID, and I don't know who it was in this class. I believe it's in this class. Anyway, a battery, if we use this fundamental definition, V times I, V taking positive to minus, I entering the terminal. This would be a positive power. Now just listen. Do y'all agree with that? This would be negative. Y'all see, it'd be identical in magnitude, opposite in sign. Now listen carefully. That means the sum of all the powers is zero. And that's always true for a circuit. What it's saying is the power supplied is the power dissipated, and that should make intuitive sense to everybody. Do you agree with that? I mean, any kind of either disagree, agree, some way of me knowing you're alive, or at least you're watching, it really helps me. Now,
so right now we're talking about it as if it's DC.
It doesn't matter if it's DC or not. You see that function of T? It's at an instant in time. With me?
Okay.
That's all it matters.
Okay. Gotcha.
It doesn't matter what the voltage and current are. At an instant in time, this is the power that's instantaneously dissipated or used. Now, it can be negative, that's supplied, and it can be zero. Now, look here. If we assume for steady state analysis, and when you see the word steady state, I want you to follow me here because you're going to get real confused if you read a lot of stuff on the internet or even in your book if you don't listen here. Steady state does not mean it is DC. You all hear me? Steady state means at a constant frequency where the actual operational frequency doesn't change. Coming out of your wall outlet, the frequency is 60 hertz. It means there's 60 cycles or 360 degrees of change cycles per second. That's what a hertz is. And it's 1 over the period, really. And that also means that it is changing with time, but it's considered steady state because the frequency isn't varying. Did everybody catch me on that? Class? Got me? Even though it's a voltage that varies with time, they consider that steady state because the frequency doesn't vary. It's a standard in industry. And I'm sure mechanical and industrial and civil, if there's anybody there in civil, or fiber and polymer, or aerospace, or everybody is going to have an equivalent to that, where something is actually wobbling or moving at a constant frequency, and you look at as a non-transient event. Now, the way you always deal with things that have a voltage and current that varies as a cosine of omega t function, they have to be at the same frequency, by the way, if this is a linear time invariant circuit, is you find the instantaneous power by multiplying the two, correct? Now, there's a lot of slop here. There's a lot of, I guess, room for adaptation. The voltage is unknown. The current magnitude, VM, is unknown. I'm sorry, Vm, the voltage magnitude is unknown, so is the current. The omega t is the one thing that's constant with these two waveforms. And the angle the voltage is at is not known, or the current. Let me say this too. How would you take this V of t and turn it into a phasor? Can anybody answer that question? Remember, phasors are what we used when we dealt with steady state analysis, right? You all remember that? Where the inductors were J omega L and the capacitors were 1 over J omega L as far as their AC resistance. How many remember that at least? Guys? Okay. 1, 2. All right, real important you do. If you don't, you need to jump back and review it because you're gonna get lost here in a second. All right, if I change this to a phasor, I'm not gonna call on you, but what would you do? You would say this would have a magnitude Vm, right? And it would be at the angle theta V, wouldn't you? You remember that?
Yes.
And if you change this to a phasor, it would be magnitude Im at angle theta I, and you would suppress the omega t. The omega is only used to calculate the phasor impedances, the 1 over J omega C, right? And the J omega L. That's it. You got that? Now, if you look at this, just listen now. If this is the voltage, this is the current, and again, the angles are undefined, the magnitudes are undefined. So we can adapt this for anything. Then the instantaneous power is this. Do you all see that? Right? You'll notice what we have here are two cosine waveforms that vary at the same rate. The omega is the same. Now this is the point of the whole thing. Once you do that, this is a cosine identity. Cosine A, cosine B, it's 1/2 cosine of A plus B, 1/2 cosine of A minus B. You remember this probably from the days when you had to do it with trig and stuff like that. It's a simple cosine identity. Therefore, the instantaneous power is this. And here they replace the omega t plus theta V right here for theta 1 and the omega t plus theta I for theta, or for phi 2. And then they went and broke them out here and you get this. Do you all see this? Good with? Now, hear me now. And if some of you guys can come back on video, it would be helpful to me, but you don't have to. And I can't force that issue. Anyway, with this, the one thing you'll notice, he plots this over here. Y'all see the power right here? And this, I'm trying to show you the power. Right. That's wrong. Maybe it isn't. Let's see. What it should be is that the power itself right here is going to have an average value that's non-zero, but it'll have this variation. You see how this cosine of omega t plus theta v plus theta I, right here, that varies, right? And last time we mentioned that the average of a cosine waveform over a period was 0. Do y'all remember that? How many do? At least I try to direct your attention to it, right? The average of a cosine waveform is 0. So when you take the average value of the power, this portion of the trig identity for P of t goes to 0, and you're left with this. Do you see this right here?
Yeah.
Now I'm going to get to some hardcore examples and not spend a lot of time wading through this, but y'all see what I'm up to. So if we're talking,
So does that whole thing in the brackets go to 0, or just the cosine?
just this portion when we take the average. The instantaneous has this, doesn't it? But when we take the average, which we're about to do, all right, we're going to find out this term goes away because we're worried about average values always, okay? With me? Now, here, he gives you a hardcore example. I'm only going to touch this briefly. I hope you looked at it. Here, I'm going to assume V of t is 4 cosine of omega t plus 60 degrees. All right. And the load here, so he's saying this is the voltage right here. Do you all see this, class? By the way, did somebody message me about COVID? Was this you, Gabby, or not? No? Somebody, is it Mandy? Are you in here with COVID or something? There's somebody that sent me a message. I'm trying to figure out who it was. And I just saw a COVID thing pop up. All right, well, if you have it, you don't have to share it with everybody, literally. But I'm just telling you I'm aware of it, and I'll get to it later. Getting back to this thing. Here's the Z he gives it to you. Remember, Z is at that frequency. It's probably an inductor and a resistor because it's got a positive phase angle in series. That's what that Z is. Here's the voltage they put across it. This is the kind of problem on a final exam I give just to find out if your head's on straight, because people at cram don't know what to do with this. All right, now what do? We take this and we turn it into a phasor, right? Right? That voltage is just forward 60 degrees, isn't it? Look, 4 magnitude, 60 degrees angle, right, class? Y'all hear me? 4 at an angle of 60 degrees. And I appreciate everybody that turns on their camera. All right. And if you're eating lunch, I don't care. It really doesn't bother me. It doesn't matter unless you're, you know, if you're drinking down beer after beer, keep it muted. But anyway, try to follow me on this. Now, if that is the impedance, that's the phasor form of the voltage. This is, can you all see the cursor hand, by the way? What I got here? Yeah. All right.
Yeah.
This will give me the current, right? Now listen, that angle 30 degrees is the same angle that would go here. And that means I of t in the time domain would be 2 cosine of omega t plus 30 degrees. Do y'all follow me? That's phasor, that's time based on the voltage. Got me?
Okay.
All right, I wish I could print these off and send them to you, but I can't. Now, this is the phasor information, but the instantaneous power here, and you won't need to know this, the instantaneous power given right here, if you look at this, it'd be Vm Im over 2, Vm Im over 2. 4 times 2 is 8, divided by 2 is 4, right? Then it's going to be times the cosine of theta V minus theta I, or cosine of 30 degrees, right? That's 0.866, right? Or square root of 3 over 2. You don't have to know that, just go with me. Plus this, which is the magnitude of what? It's going to be Vm Im over 2, 4 again, cosine of 2 omega t plus 90 degrees. He's just showing you what it becomes. And then he plots it. Here's the power, here's the current, here's the voltage. Now, the average value of both current and voltage is 0. Y'all follow me now? If you, because what? Current and voltage have a cosinusoidal dependence, right? Cosine of omega t. Both of those will have an actual average value of 0, but not so with the power. The power will have this average value, 4 cosine of 30t, or cosine of 30 degrees. Y'all follow me? I'm talking fast, and I don't like doing it, but I want to make sure you understand. Got me on this, class?
Yeah.
All right, now, next page. Here, I'm not even going to go through this integration because it's a straightforward integration of this portion that'll give you a 0. Here's what's important. The average power here will be given by this equation. All right. Or simply put, for the prior example, it's equal to 12.5. Wait a second. That's not the prior example. That's this example. If we do this, we would just have 4 cosine of 30 degrees, which would be the square root of 3 over 2 times 4, or it would be 2 times square root of 3 would be that value for average power. Now, we deal primarily with average power when we're dealing with power circuitry. You hear me? You deal, the quantities we're going to be talking about are average power, not instantaneous. That's why I'm not going to do any problems with instantaneous power. They're laid out here. Here's something to note. If the voltage and current have the same phase angle, then the cosine of 0 is 1 and the average power is just 1/2 Vm Im. That is for AC. That's for a constant frequency though. You hear me? That is not true for DC. This is AC, or alternating current and voltage at a constant frequency. Now, if the difference is 90 degrees, then you're going to get a cosine of 90, which is 0, and you get nothing. Now I'm going to make it real to you. And here I'm going to go to the document camera. All right, this is your first time you're stepping into the world of applying the theory. So my document camera right here, and I'm going to slow down. I assume everybody can see it, right?
Yes.
All right,
Yeah.
here's the deal. If you have a resistor and you have a current I of t and you have a voltage V
You
of
need to move
t,
your paper up a little bit. And it's out of focus.
back in focus now, right? This is a resistor R. If we take a look at the instantaneous power P of t here, we see that's going to be V of t, I of t always, always. And if we assume that both voltage and current, both V and I, have a cosine of omega t plus or minus a phase angle, in other words, that's the formal variation, then this instantaneous power right here for the resistor will be Vm, that's the magnitude of the voltage squared divided by R, times cosine squared. Well, actually, I can just do it this way. Times cosine of theta V minus theta I plus cosine of 2 omega t, this is in the prior slide, plus theta V plus theta I. That's just in the prior slide. That's the instantaneous value of P of t. For a resistor, the average value, capital PAV, this is the average power in a resistor. Please watch this. This is the one we worry about. The average power, and this is strictly for a resistor, so I'll put an R here, is equal to either 1/2 the magnitude of the current through the resistor squared times R, or it's equal to 1/2 Vm times Im, or it's equal to 1/2 times Vm squared divided by R. Now, all three of those are equivalent. And here, both Vm and Im are the magnitude in front of the cosine of omega t plus or minus the angle for both I and V. Does everybody follow me on this? And I know
What is the subscript M for on I?
magnitude. It just is positive, magnitude. Y'all hear, you hear me? That's all it means. Now,
I hear you.
that's for a resistor. This is what we worry about. For both inductors and capacitors, they have non-zero average power. For both inductors and capacitors, and here I'm just going to put L here. And really, the only thing I care about is the average. The average power for an inductor or a capacitor. Nope, let me do it this way. Let me move this up. This would be for a capacitor, average power, and that's what you worry about, is 0. For inductor, average power is 0. It has an instantaneous power, but we don't even worry about that. That's just the current times the voltage. It'll go way up to a positive value, then way down to a negative value. And it'll swing back and forth such that the average value is 0. Now, I'm going to make mention of one thing to give you perspective. An inductor and a capacitor are an energy storage device. How many have heard of supercapacitors with exotic materials? If you're in materials science, you may have. Has anybody besides me, you've heard of it? Joseph,
Yeah.
anyone else? Amanda? All right, what a supercapacitor is something, Andrew, thank you, that can store a phenomenal amount of energy because of a dielectric material that is very large. And I'm not going to go off onto how a capacitor stores energy here. That's later. But a supercapacitor can store all sorts of energy, and it can give that energy back with very little dissipation. But ideally, if it was an ideal supercapacitor, it would have 0 dissipation, and that causes a problem. It means when you short it out, it could have an infinite current. I mean, the current could go to infinity very quickly, and that would cause the wire to blow up and stuff. I'm just mentioning this for some perspective on problems with these things. And capacitors do blow up for a lot of reasons, and I'll get to that. Anyway, the average power in both of these is 0. Now I want to jump right into an example to try to showcase this. Are you well with me? We're worried about average power. Let's do something where this is the kind of problem Baginski would throw in a Monday quiz. Let me restate this. This is the kind of problem you can expect on Monday. Y'all hear me?
Yes.
So it is time to pay attention and turn off ESPN or whatever you're watching, the French Open. Now, here I'm going to give you a voltage source. 12 cosine of 40t plus 30 degrees. Now, I could put that 30 degrees. It should be in radians, but I'm leaving it as 30 degrees for a reason. So it'll be easier to work with. We know if we actually did a calculation, this would have to be in radians, 30 degrees, right? It would have to be what? Pi over 3, right? Or excuse me, pi over 6, my bad. You got me? But don't worry about that. I'm going to leave it 30 degrees because you're used to seeing degrees. This is going to be V of t. Now I'm doing this. Now listen carefully. I'm going to put a resistor here of 20 ohms. And I'm going to put an inductor here. I'm going to let L equal 1 Henry. And here's what I want. If this is considered a single element, I want the power dissipated by that element. Now, y'all hear me? You're going to start putting together stuff. Y'all hear what I want. I want I'll make it average power dissipated by this boxed element. Can y'all follow me?
Yeah.
Mm-hmm.
Thanks for coming online. Haley Elizabeth Stone, thank you. All right, follow me on this. You must be at the library or something, or wherever you are. Anyway, follow me on this one. First thing you do when you do a problem like this, these things always scare people. Take it into the phasor domain. You all see it's a cosine of 40t. That's a constant, isn't it? That's a constant frequency, right? Frequency doesn't change. So now I'm going to redraw this in the phasor domain. Got it? Y'all hear me?
Yes.
Yeah.
All right, in the phasor domain, first thing I do is take this and make it a phase. Well, let me do one other thing. Not Jessica. Somebody else, tell me what omega is. And not the two, not Gabriel or Gabby and her friend, somebody else. John, you can respond. Or anybody else. I wish I didn't say that.
Isn't it 90?
Can you see that? That was meant to be 30 degrees. If you're saying that angle, that's the, oh, you said 90? Oh boy, you can't read my writing. This is supposed to be 40.
Oh,
That's my fault, Amanda, my fault. That's meant to be a 40. Got me on that? But you're right. This is 30 degrees, that's 40. So my point is, and you're right, and thank you for my pointing out how bad that looks. Omega is 40. It's radians per second, right? Now just listen. You okay with that? Now, with that in mind, I can replace this inductor with its impedance, can't I? You agree with me, everyone?
Yes.
What would it be?
So the JWL, so 12.
J omega L, or it would be what? J omega 40, right?
Yeah.
Times L is 1, or J 40 ohms, right?
Mm.
Can you all see that? Sorry, it was meant to be a 40, not a 90. Agreed?
Yes.
All right. Now I'm going to redraw it for a reason. So I've got a voltage source here of plus to minus 12 volts at an angle of 30 degrees, right? We get rid of that omega t business in the cosine, correct, class? We're now in the phasor domain. Next, we put 20 ohms here. And over here, we don't put L equals 1. We put an inductor here. And the value of that impedance on the inductor is J40. Do you agree with me?
Yes.
My next step is calculating this current. It's a phasor current, right? This is the phasor voltage. Dr. Gross and Dr. Irwin doesn't do this, but Dr. Gross puts little tildes if you're looking at his book. And I find out that that current is what? Sorry, that current I is equal to this voltage, right? 12 at an angle of 30 degrees
Mhm.
divided by this, what? Impedance, right? Which you'll notice this is going to be in what? Rectangular. It's a Cartesian coordinate system or rectangular system. It's 20 plus J40. Now, that means I have to take that and turn it into a magnitude and an angle. Can anybody do that for me? So I have 12 at 30 degrees, and then I have this. Anybody? Anybody have a calculator out there?
Yeah, I'm working.
Can you move your pen? Thank you.
All right, while you're working, and I hope you have your calculators. I usually in class, I just call out for people to do this. I don't spend time on octave doing it. I will if it's necessary. I just need a magnitude and an angle here for 12 or 20 plus 40, J40.
44.72 at 63 degrees.
What did you say? Say that again.
44.72.
That sounds right. Anybody confirm that?
Yeah, the magnitude is 44.7.
At 60 degrees or just 60 what?
63.43 degrees.
That sounds right. Are you with me, class?
Mhm.
Now, if that's true, what now will be the actual phasor value of I? It would be 12 over 44.72, right? What's that? It's what?
.268.
Okay, and what's the angle going to be? Now listen, that would be 30 minus 63.4, right?
Mhm.
So it'd be minus 33.4, is that right? Y'all agree with that?
Yes.
All right, that's the phasor current. Now this is the beautiful thing. I'm asking for power dissipated. I'll say it again. I'm asking for power dissipated. Average power dissipated at that, right? That's up here. What's the average power dissipated by that inductor? Anyone?
Zero.
It's 0. If it was a capacitor, it would be 0. Either one cannot dissipate power. What can dissipate power? That resistor, right?
Yeah.
And the power dissipated, and listen to me, is easiest to get by just saying this power dissipated by that 20 ohm is simply 1/2 the magnitude, not with phase angle, just magnitude of the current squared times the resistance. Now, specifically for our case, the power dissipated by that 20 ohm will be equal to 1/2, right? Times the resistance is 20 times I squared. Well, this is I, right? So I would take I and square it. It's a magnitude. That angle means nothing. So I take that and it's 0.268 squared. And that would be the power. And the units are watts. Now, can somebody give me that? Really, it's 10 times whatever that is squared. Anybody? Anybody at all?
0.71.
0. Say it again.
0.718. 0.72.
I also got that.
0.71.
Yeah, 0.718.
All right, good enough. And that would be watts, a little less than a watt. Now, the only thing I really did, and it's now you're going to see the simplicity. When I got this problem, the panic would set in, well, I don't know what to do with this. Just make it an impedance, J omega L. It assumes, go ahead.
Sorry, can you repeat why the power in the J40 is 0?
The phase angle between current and voltage will be exactly 90 degrees. I'm going to just show you this, but I'm going to flip the page. Has everybody got this? Matter of fact, let me just go down here and do it, and I'll show you. If you have an inductor, let me do an inductor first. All right. And inductive impedance is J omega L, right? Now suppose I put a voltage across it. All right, and say it's V and just at an angle of 0 degrees. And I want to know what I is, okay?
Mhm.
All right, I here would be equal to, well, J omega L, first I would take this voltage. It's V at an angle of 0 degrees divided by this. Well, that's really what? Omega L at an angle of 90 degrees, correct?
Mhm.
That's, I would have a magnitude of V, right, over omega L, and it would be at minus 90 degrees, correct?
Yes.
All right, now that's the voltage, that's the current, right?
Mhm.
Bear with me now. So when I look at the power, the average power,
Yeah, I got
right,
it.
it's going to be cosine of theta V minus theta I. That's cosine of 90. Do you see that?
Yes. Mm.
Cosine of 90 is 0. That's why an inductor or capacitor does not dissipate. It stores energy and it returns energy into the system, but it does not dissipate it. Now, in fact, yes, there is some small, minute amount in any real capacitor or real inductor that is dissipated and has to do with heating. The elements will heat. That's the reason. But
Okay.
that's included in a more complicated model. Now, I'm going to leave this up here, but that means we did the power on this one. That's a very practical problem. And again, I could make it very complicated by adding a capacitor in series with that inductor, right? I'm joking now. What would happen? Let me just bring that back. What would happen if instead of this, somebody give me a hand on this, instead of this, I put a capacitor in here, right? Now what would happen? Anyone?
Zero change.
Well, how would we deal with it? Well, down here, what would happen? If there's a capacitor, I'd have to put in an element that represents it, right?
Mm-hmm.
And that capacitor would have an impedance. And the impedance of this capacitor would be 1 over J omega C, or simply minus J over omega C. Correct, class?
Mm-hmm.
And then when we figured out the current, we'd have to take J40 minus J omega divided by omega C. Correct, class?
Yeah.
So you would have to adjust the reactive component. How many see that? Now, if I did something really diabolic, and I put another element here, say this was a resistor, how would it change? And I still want the total thing dissipated by the circuit that's attached. Anyone? Let me ask you this, would the voltage change across that prior circuit if I put if I put an element here, class? Go up here and I'll do it. Suppose I put a resistor here. Doesn't matter what the value. Would anything about this circuit change the current? Because the voltage is the same, right? Y'all see that, everyone? The voltage is the thing that drives current. Now, the addition of this resistor does one thing. It causes current to flow here, right? There's more current from the source, and it would dissipate power. Do y'all see that?
Mm-hmm.
Yeah.
Everyone? Here's a question. Would anything change if this wasn't a resistor, but a capacitor? As far as total power dissipated, class?
Would it be the
Let's try.
same thing as just adding the first resistor?
No, a capacitor does not dissipate power, average power. That's my point.
I mean, adding the first capacitor.
If I
So like
put
adjusting the reactive element of the inductor.
no, look, when I'm looking for
Number.
this current here, this capacitor has no bearing on it because it's in parallel with the voltage, right?
Okay.
All right, that I can put anything in parallel with that voltage source and has no bearing on what happens in that portion of the circuit. Nothing at all.
Mm-hmm.
All
So
right.
whatever power was dissipated is still dissipated. And adding a element here, whatever is dissipated by that element will be added to the average power dissipated by this. That's my point. Y'all follow me?
Yeah.
Okay. Let me go back to the PowerPoint if I can. And I don't like them either. Now, this example is the same thing we just did with slightly different values, right? He gives you 10 at 60 instead of 10 cosine of omega t plus 60 degrees. He puts it right in terms of a phasor value. I'm likely to do that too. Do y'all hear me? I'm likely to present it that way, just like you've seen it before. Here you've got 2 ohms in J2, right? Very quickly, if you're asked for the power dissipated, you would first calculate the current, as he does. There's the magnitude 3.53. And after you calculate that, you can go through and do this if you want, but you don't need to. You can just simply say, well, the power dissipated will be 1/2 times the magnitude 3.53 squared times the resistance 2. Do y'all follow me?
Mhm.
You don't need to include this to anything else except for the current calculation. Once you have the current, you have the power dissipated, and you can prove that if you'd like. Y'all agree with me, class? Because power has no phase angle. It's strict real, at least not yet. It doesn't. This is average power and has no phase angle. Now, you'll notice he's going to mention this over and over. Since inductors do not absorb power, it's average power. In fact, they do absorb instantaneous power, but all the instantaneous power that's absorbed is put back into the circuit. So that statement isn't 100% true. We good on that?
Yes.
All right, next one. Here, the circuitry gets a little more complicated, but the essence of what I'm going to ask will not be. It says, determine the average power absorbed by each resistor and the total average power supplied. Well, there's 2 things you worry about. Whatever is absorbed by all the elements of the circuit is supplied by the source. Y'all hear me? Now, I can be more formal about it if there's 2 sources, but for now, whatever is supplied is dissipated. It's that simple. There's no mysterious storage device if you're in steady state. So if I look here and I want the power of this circuit, now this is kind of a classic problem I might throw at you on Monday, that I might give you on Monday. Got me? So pay attention. So how would you do this? I know the solution's before you, but what are you going to look for? It's current, right? Now you could do this, and matter of fact, here's the thing you got to watch for. If they just wanted the power in this one, the 2 ohm over here, then you could do a source transform here. All right. I mean, you could do it several ways, but if you wanted just the power here, frankly, you've got a voltage. Now look at this, class. This is something I want to point out. If they just wanted the power through the 2 ohm, and I kind of do this stuff routinely to see if you're paying attention. I just want the power through the 2 ohm. Do I care about any current here, class?
No.
No. If I just want the power here, I could care less what happens over here, right? Do I have enough information to get that power? Well, what do I need if I'm after power through a resistor? Current through that resistor, right? And what dictates current? The voltage across the elements in series. I've got 12 at 45 is the voltage. It's in parallel with 2 minus J1. So I can calculate this current, I2, can't I? Simply the voltage, 12 at 45, and then divide it by 2 minus J1. I can get the current. Once I have that current, I take the magnitude of that current, square it, multiply by 1/2, and then by the resistance, which is 2. So it's really just the magnitude of the current squared. That's if I wanted just this power. This wouldn't matter. You remember from the prior quizzes, a lot of times if you knew what you're doing, there were essentially no-brainers in terms of you would just have to sum voltages. Like the first quiz where I had 2 voltage sources and I want a voltage across an element. If you would just sum around the voltage sources, you got it. Some people, I think, instinctively solved the whole 9 yards of that thing, and they wasted time. The only thing I was after was a simple voltage. Some of you remember that, don't you, at least? Right?
Mhm.
All right. That's the kind of stuff that tells professors whether you're paying attention and know what you're doing, or you're just kind of cramming and throwing it out there. Here, if I ask power there, it's not a problem. You got voltage. If I want power here, you can get it even quicker. I got the magnitude of the voltage, 12. So it's just 1/2 times V squared, or 12 squared, divided by R, 4. Okay, you could get it even faster, but that doesn't matter. This is a simple learning example. Please go through that. And if you have questions before the quiz, I'll address them. But do y'all follow me what I'm doing here? We're really just doing circuit analysis and getting the current. Isn't that right?
So because you're given V of M, you don't even have to find the current, right? For power, like you could just use V with R.
That's for this 4 ohm, yes. Just for the 4. Now,
Why not for the 2 ohm?
Because you don't know the voltage, right? The voltage is across the 2 minus J1, both loads, right? You have to get the current. With me?
Okay.
And believe me, there are no dumb questions. These are questions that need to be answered here. All right, if you got one, ask it. Face or no face? All right, now going on. Another example, what's the thing that you're seeing? Circuits are getting a bit more complicated, right? But the essence is, now, no matter what, if you have an element with a voltage and a current that you know, you can always get the power dissipated by taking 1/2 VMIM times the cosine of the difference in angles, theta V minus theta I. I'm telling you that. Here, if they want, what do they want? Find the average power absorbed by each resistor. Well, how would you do this on a quiz? Let me ask that to the class. Joseph and Jessica, you respond all the time. And John, not you either. Somebody else just respond. If you were given this, where would you start if I wanted the power dissipated by the 2 and the 4? What essentially do you want? What information do you want? Well, it's the current, isn't it? The current through either element would do it. Do you all agree?
Yeah.
Now, here's how I do it. I don't care how they do it. I'm just telling you how I do it. If I want the current, here's what I'm going to do. I'm going to get this current right here with the red line here. You all see that? That's the total current. Once I have that current, I've got this power. It's just 1/2 that current's magnitude squared times 2, or really it's just the current magnitude squared, right? The 1/2 and the 2 cancel. Correct, class?
Yes.
If I'm going too fast, let me know. Okay? Now, down here, how do you get this current? This is what I would do. I would do current division. If I got this current, I do current division. You can do it with complex numbers. Current division says if I want this, I take this current, I multiply by the opposite impedance, which is minus J4, right? Then I divide it by the total, which is 4 minus J4. So then I get that current magnitude, right? And then I would take the magnitude of that, square it, multiply by 1/2 and multiply by 4, and I get the power. Now let's see how he does it. He says, well, this impedance is really 2 times, this is the parallel combination of this 2. So he gets the total impedance and he's got it here, and the total impedance is this. Don't worry about calculating it right now. Do y'all follow me?
Yeah.
I mean, do you? That's the total impedance. To get the current, I divide that voltage by the total impedance, and I get this as the actual current. And if you have your calculators, you want to try it, do it. Because your calculators will cause you more headaches if you don't know how to use them. You'll lose a whole lot of points, and really you'll be mad at your calculator. Learn how to use your calculator efficiently and don't make mistakes with degrees to radians and things like that. Because you're going to do this, and I'm warning you right now, very little forgiveness, if any, for that. That is an error that's really unacceptable. It's like dropping a pass in the end zone when it's literally an underhanded pass. You can't do that. So here, I have this current, that's this current. Therefore, I have this power, 1/2 the resistance times the magnitude squared. Now for I2, what he does is what I suggest. He uses current division. He takes the opposite impedance, minus J4, over the sum of the 2 in parallel, and he multiplies by this current, and he gets the source current. He gets, this is I2. And then he says the power through the 4 is just 1/2 times the resistance times the magnitude of the current squared. Do y'all follow me? It's straightforward. With me, here's where the problem lies, your calculators. And I'll see this. I'll see people get this value right here, I, and they'll have it like in a real and imaginary portion. Do y'all follow me? Now listen to me carefully. They'll have a real and imaginary portion. Then they'll square that. Now take the magnitude and square that, and they'll get the wrong answer. Do you hear me? If you have like 1 plus J1 and you square it, what do you get? Well, you're going to get 1, right?
Mhm.
Then you're going to get -1, right? Or 0. And then you got what? J1 times J1 or 2J1. That's the wrong answer. Do y'all follow me? The magnitude of 1 plus J1 is square root of 2. All right? Squaring that is 2. Got that, class? So beware of that one with your calculators.
Yeah.
You go with that? Hang on. All right. Now, this is just another problem where what? Where now it gets even more complicated, right? And by the way, this is a current source. I'm going to skip down here. It's just showing levels of complexity. Now, these are all learning examples. That's why I like this. And I hope you understand, I'm not a PowerPoint kind of guy, but I don't have a board to draw on. And I really don't have you in front of me. So I'm just dealing with what I have. Got me? Everyone?
Yes.
Yeah.
Hang on. It goes down. And the last thing I'm going to mention that you are not responsible for on Monday is this. That the maximum average power transfer, if you have, and this is real important for MEs and aerospace engineers, so hear me. I mean, super, super important. If you're over an ME and you have Birch or some of these other people, there's an equivalent mechanical. Aero, Joe Mazdalani's there, there's a few other people. They have an equivalent in aero, but I'm not going to spend time on it now. If you want the maximum power transferred through a system and you have a voltage that has some equivalent impedance in front of it, just hear me, and you want to figure out what load would maximize the power transfer to it, the load will be the conjugate of the Thevenin impedance right here. Now, what does a conjugate mean? If your impedance here was 20 at an angle of 30 degrees ohms, with me, 20 at an angle of 30 degrees, the conjugate is 20 at an angle of -30. Y'all hear me? You know, how many know what conjugation means from your mathematics courses? You good? Okay. Now, so here, he's going to ask you to calculate maximum average power. I wouldn't worry about that too much. I'm at 1:51 and my class is over. If you want to stay for an office hour, I'm just going to touch on a few things. But you may go, and I apologize that I can't spend more time with everyone, but I'm really trying. Did this help, by the way, these PowerPoints? Or not?
Yes.
I thought it was super confusing.
How many understand them now? Thumbs up, thumbs down. You like it? All right, good. The girls like it because they can read it.
Oh no, that was us agreeing with Joseph. Sorry.
What? You're against it?
We also thought it was super confusing, not gonna lie.
Well, how about now? Is it any better?
No.
Well, it's kind of a punch in the face with a whole lot of stuff.
It's
Yeah,
not
but-
any better.
Once he goes over it, it becomes more clear.
Oh yeah.
Do you understand what I was doing or not?
I would say I know
Like,
more,
I
but do I
didn't-
know a lot? No.
Like, I didn't understand what you were doing until like the last 5 minutes of class, and then it like clicked where, oh, it's just P equals RI squared. It's the same thing with
One
just ugly
half,
numbers.
one half.
Whatever. But it's just the same thing with ugly numbers.
Ugly,
I didn't
yeah.
get that until the very end. And I was like, oh, I wish I'm gonna have to rewatch the lecture with that understanding.
Any other comments? And believe me, it's good to hear. You can go ahead and insult away. So next time, get better glasses. You can say anything you want. It doesn't matter. Feel free. This is your shot.
Oh,
Are there
the
two
reason
cameras
you're
on
so
there?
dark is because your window's open and it's
Yeah, I know.
camera's
But
auto balancing to the brightest light source.
I really don't care. I mean, I'm just trying to, you can see what's over there. That's the only thing that's important. Okay, now I want to tell you one other thing. Since I've got your attention, and since it's super confusing and it doesn't make any sense, I'm going to try to ask you something that will tell me where the confusion lies. But I'm going to do something. I'm going to shut that down. This is for all the people that are super confused. And I like that word. It tells me it's essentially a waste of time for me to do PowerPoint. But I still believe in that case, they were good. I think they helped. Honestly, they did, whether you like it or not. Now, getting back to the issue that everybody has. I'm going to put up a bunch of problems, as you might have guessed for you. And I'm going to ask you to do all the problems by Monday. And they're going to be essentially just circuits problems. You're going to solve a circuits problem. Y'all follow me? It's
Yeah.
not going to be hard, but then you have to know what to do with that information to get power. Now, when I say circuits problems, some of you are wondering, like before, just like before, AC circuits problems. So, and I'm not going to blind you with science or anything. I'm going to try to keep this as simple as possible. You guys ready?
Mhm.
Y'all get your lunch and your coffee and
Yeah.
everything. I'm drinking coffee too, so I haven't had my lunch, but I will survive. And I had a nice run this morning, so I'm in a good mood, kind of. I hope you all exercise in some way, shape, or form because it'll help you in the long run. Probably help your mental health too. I know it's out of focus. It's coming in focus, right? How about there? Now, can y'all see 510 that I've shown you? I'm going to put these problems up. Y'all hear me?
Yeah.
I want you
Yeah.
all to listen. Don't worry about the conservation of power. That says that all the power that's dissipated by the elements is supplied by the sources. But I don't remember I said power, negative power is a supply, positive power is a dissipation, right? Let me just get to the essence of this thing. If you wanted to know how much power was dissipated, first thing is how much power can J1, an inductor, dissipate? Average power now.
0.
Yeah, that's what I'm looking for, 0. What about that capacitor? How much average power?
Also 0.
Exactly right. Now, what am I looking for in this circuit? You're right. These two don't dissipate. What about this 2 and 4? They dissipate power, right?
Yeah.
So what do I need? I need the current through them, right?
Mhm.
Now,
Yes.
listen to me, because this is essentially a circuits problem that you have to be able to solve well. I've told you before, everything we do is based on your understanding of prior concepts. If you don't understand circuit analysis, you'll never understand power because it gets really complicated in a little bit unless you have a thorough understanding of circuits. Then it's easy. But if you're going to do this one and I leave it to you to solve, here's the thing you watch for. You can never transform that element and then calculate the current through it and use that current. You got me? You
just
can't
kind
use a
of-
source transform to calculate that current. In other words, that stays alone. However, if I wanted this current, I could do a source transform there. Y'all hear me? If I wanted this current. Y'all? Now, I know that
You're
that
kind
J1 doesn't.
of skipping out, so I've missed a couple words there. Could you say that again?
Is it really? Can you? Y'all can hear me, can't you? Is it? I was speaking too fast. Can you hear me now or not? Klaus?
Yeah.
Yeah. Let me know if there's an audio issue. Everybody's jumping ship. Okay. Here's the way I would recommend you do it. If this is given to you, probably the single easiest thing to do is nodal analysis. Now, by nodal analysis, if you put a node right there, in this case, because there are 2 elements we need the current through, correct?
Yeah.
If we want power dissipated. Y'all hear me on this one? I'm after power
Yeah.
dissipated, average power. So what I'm going to do is I'm going to get a voltage here, right? One equation, one unknown. Are you with me?
Yeah.
I'm trying to
Yeah.
save time, so just listen. Now, if I put a ground there, and I did, wouldn't I get the current through here? It would be 12 minus V, right, over 2. I'm trying to talk very slow. 12 minus V over 2 ohms would be this current, right?
Mhm.
Mhm.
This current would be equal, oh, sorry, not that way, this way. That current would be 18 at 30 degrees divided, or 18 at 30 degrees minus V over J.
Yeah.
Over J1, right? Now listen, that's complex numbers. Y'all hear me? It would be what? It would be 18 at an angle of 30 degrees minus that V here divided by J1. J1 is 1 at an angle of 90, right? You got to get good with complex numbers. That's what that current would be. And it would equal this current, right? Coming through here, which is just V divided by 4 minus J1, isn't it?
Mhm.
Yeah.
And you could solve for V. That's one equation, one unknown, correct, class?
Mhm.
Yes.
Now, once you solve for V, you could therefore go back a step and calculate that I and calculate this I, right?
Mhm.
Are you with me?
Yeah.
Yeah.
And once you have that, you know the power dissipated by 2 ohms is 1/2 I squared R, right? You just put 1/2 and 2, which you cancel. It would just be I squared here. And the power dissipated by this is just 1/2 times 4 times the magnitude of that current squared. And that current would be just V over 4 minus J1. Now, you can see that the secret to this thing is making sure you get the magnitude of the currents correct.
Yeah.
All right.
Because that's the most important.
That's what you got. But you can see it's just circuit analysis from there, right? I mean, before that, it's circuit analysis applied. And we're going to do a lot of circuit analysis when we get to power, especially 3-phase power. Now, all the problems I'm going to give you are in the first, they're 1 through, I may give you some out of another book too, 1 through 13 here, but I'll selectively give them to you and I'll provide the solutions. But they are primarily circuits problems. Now, I'm going to say one last thing before I take questions. I would advise you to learn how to efficiently use your calculators to solve problems with complex numbers, especially if it's a 2x2. All right. If it's just a one single equation, make sure you can do it efficiently and accurately. And the best way to do it, in my opinion, is just work a whole lot of problems. Don't look at the solutions until you got the answer, then look at the solutions. Now, does anybody have any other suggestions for the good of the group about how to solve these kind of problems? Because I'm open. I gave you my best shot, and I've taught this for years.
It's just a question. So you were saying that basically when you have a capacitor or an inductor, power doesn't go through there. You will have to calculate the power through the resistor.
Average power is not dissipated by that element, but the current is limited by those elements, the current that goes through a resistor possibly. That's the reason you always have to calculate the current in a circuit, and then you go from there, okay?
Okay, yeah. Current, when calculating current, we were going to consider the capacitor and the inductance, but when calculating power, you just have to look at the resistor.
Average dissipated power is based on the current through the resistor.
Okay, okay.
Now, y'all, hang on.
Can you break it up by meshes? Like if you had a...
Yeah. What you're saying, wish I didn't close it. Sure, what you're saying is if I look at this, Dr. Baginski, it's easier to do it with loop analysis, right? Or mesh analysis, correct?
Yeah.
Let me do what you're saying. And you're absolutely right. You could do it. You could easily do it that way, but you're going to get a 2x2 then, right? Now you're going to get a loop here and a loop here. So you have I1, I2, so you got a matrix math, right? You got a 2x2, don't you, class?
Yeah.
Otherwise, I just had one equation with one unknown. That's the only reason I chose nodal.
Okay.
Bless you. Okay, everyone? Now, something else I'm going to say about these problems. No matter how much I say this, I don't think, well, I worry that I'm concerned that people will not take me seriously. If you do not know how to use your calculators, you'll get almost 0 points. Can I be any clearer? If you write an equation, you have to know how to solve that equation, or else you're not a very useful engineer. And if it was in my power to give you octave and have everybody with octave right there, I would, but I know I cannot allow that kind of stuff in class. What I'm getting at is this. You have to know what you're doing with a calculator or computer electronically so you don't mess up. That's my one point. Now, y'all got different kinds of calculators. There's no one standard calculator. You cannot use a phone. You can't use a wearable electronic device, but you sure have your calculators. And from what I gather, most people have TIs in here. I have yet to see an old HP or an Agilent there's Casio, but I don't think any other kind are here, are they? Any other questions regarding what was presented in the PowerPoint? Because I gave you, not a lot, but I gave you some things to look at, right? I gave you, let's see, we went through here, then here, right? We didn't do this one, we didn't talk through it, but you can see the actual value, correct, class? Where they get it?
Mhm.
Any questions about this one?
Let me find it.
Now here's a two source problem. And again, when they say supplied, then they take I times what? I times V, but the polarity becomes an issue because here, if you take a look at this right here, if I want the power associated with this element, it would be magnitude of I3, right? But you can see it's flowing in. So there'd be a negative sign in front of the magnitude, angle of I3 times magnitude of the voltage times angle of voltage. So there's a minus sign associated with this. And then it's going to be what? The average power would be the cosine of the angles between them times Vm, Im, and it would be minus here. So how does he do it?
Says power absorbed.
Power absorbed or supplied. If it's negative, it's supplied, isn't it? Remember, Miss?
Oh, yeah, it would be supplied because it's power leaving the. It'd be opposite directions for the arrows, right? If
Well,
it were all
here-
positive.
Think of it this way. A source supplies power. In a sense,
Yeah.
it absorbs negative power.
Okay.
All right, I'll get to that later. But you can see, here it is. This is the power 12 at 30 degrees. It's going to be 1/2 12 times 11 times cosine, and these are the angles, and he gets negative 54 watts, or it's supplying 54. I'll do this stuff next time. I want to just make sure you're okay with that. Any other questions? Here's your loop analysis, by the way.
All right.
Anything else? Have a great weekend if that's it. Nothing, Jessica? Nothing? Is everybody gone? All
No.
right, if y'all have nothing, have a great weekend and stay safe.
Thank
Uh,
you.
I should have asked this, but I didn't. If you have any information for the good of the group about what's going on downtown or at the university, anything like that, tell it to everybody. The reason I'm saying this is because in the past, students have had information about, I don't know, food that's cheap and inexpensive, or about places that you shouldn't go because there's COVID problems.
Mm.
Okay, well, have a great weekend. And
So Taco Bell on Gay Street has really weird hours that I can only assume are due to a COVID problem in the kitchen.
be serious. Jeez.
Yeah, where it's like, or last weekend they were open they closed at like 7 p.m. on Sunday, and they were gonna close at 8 p.m. the next day, and then they were back to normal hours, which implies to me they had like an extended cleaning period or something was going on, but then they were back to normal hours from then on. So I don't know what was going on.
Well, I don't either, but I don't go there. That's popular though, isn't it?
Yeah. It's the worst Taco Bell in Auburn, but it's still popular.
All right. Well, I want to just wish you the best, and it's good seeing everybody's alive and kicking. I got a medical withdrawal from one person, and I got another person tested positive for COVID. And then I got a weird problem. Somebody said, okay, well, I'll let you go then. You take care, guys. Stay
Have a
safe.
good one.
Thank you. Everybody.
I'm gonna try. All right, let me see. Stop share. And then go. Did you get that whole thing recorded? Okay, good.